Okay, so when you have a sigma notation like this is a finite sum from k equals 1 to n. That's how we read that. So this is going to be an approximation for a definite integral. Now, again, remember when we do something like this with Riemann sums, these are your y values, your f of x sub i's, or in this case, f of x sub k's, which are your heights, times these are your delta x's, which are your widths. Okay, so you can kind of deconstruct it, if you will, like when you take your Big Mac home and you take it apart one little piece at a time to see really what is in a Big Mac. I don't know if that analogy makes sense, but anyway, let's start with your delta x. Delta x is b minus a over n, and so that's where the n comes from. So that means that b minus a must equal 10, right? That's what that means, which means that this is our width of integration. We're integrating over a 10 x value span. All right, so that might help us. And then we come over here and we look at underneath. This is going to be our starting. This should be your starting x value of integration. So based upon that piece here, let me use a different color. Based on that piece and this piece over here, you should be able to figure out your intervals of integration down here, because we are going to start with the 2. So that's 2. And then I need to integrate up to where to get a span of 10. I need to go to 12. Yeah. So that gives us 12 minus 2 is 10. Now I wanted it to be a negative so that then if the radical weren't there, then we'd go from 2 to 8, negative 2 to 8. So that takes care of that. So now we just need to figure out what the function is. Well, this is starting at 2 and then it's plus. These are just multiples of your delta x. And in this case, k is your variable of your summation. Okay. But again, that could be I, j, k. It could even be n sometimes if there's not already another n in there. And so the function, we're going to be taking the cosine of the square root of our inputs, which is just x. Okay, so that's the answer. Now, there's one other thing that we can gather from here. Does that summation up there represent an approximation for, is it a right Riemann approximation or a left Riemann? It's a right Riemann. And the way you can tell is just looking at your starting value. We're starting at k equals 1. So when you plug a 1 in for k, your first value is going to be 2 plus a width, right? So if 2 is where, like, let's say the function looks like this, cosine of the square root of x. I know it doesn't, but we're starting here at 2 and we're going to 12. But when we do our approximation, we partition this up into pieces, right? So this value here is going to be 2 plus the width times 1. This x value here is going to be 2 plus a width times 2, or 2 widths away, right? When we plug in a 1 for k, your starting y value is 2 plus a width. So that's your first value. So then you draw it back to the right. So that has to be a right Riemann sum. What can we easily do to turn it into a left Riemann sum? Just take k equals 1 to n and change it to k equals what? 0, right? You could, if your k started at 0, then when you plug in a 0 for k, your first y value is at 2 plus 10 over n times 0, which is 0. So then you're starting at 2. Okay, so that's really the only difference. So as it sits, this is a right Riemann approximation. Okay. So now for this one down here, if we want to go in reverse and we want to write an approximation in summation form for a left Riemann, well, we can say, okay, what's the width? It's b minus a. So that's going to be 4 minus 1, which is 3. So delta x is going to be 3 over n. So I know this. I know that my width is going to be 3 over n. There's your width. Times, now I just need the heights, which are going to be the y values. So how do I evaluate the function? E to the input? Well, it's going to be e to the input. E to the input. Now, what's the first value of x in my interval of integration? It's 1, right? So inside here, it's going to be e to the 1 plus, and then I just need to go multiples of the width. So it's going to be 1 plus 3 over n times, and now here's where we get to choose. Do you want your variable to be I, J, or K? Let's use I, yeah, because we've already used K. So I'm going to call this I, and now over here, it's going to be from I equals something to n. And then all I got to do now is make my starting value of I match up for a left Riemann, which means if it's a left Riemann, I want the first x value where I calculate the y value at to be at 1, not at 1 plus the width. So we start at what? 0. Yeah. And that'll do it. Okay. No, not at all. It just wants you to know kind of what the program is for left and right Riemann. No, if when we evaluate this, we're going to know what n is. You're going to be told use 4 subintervals, and then you don't have to worry about this. You can actually just do area plus area plus area plus area. Okay. Now, what's important is in general, when you take the sum, this is in general, and this is kind of where Riemann actually came in. If you take the sum from I equals, let's say 0 to n of any function x sub I times any delta x, if you then take the limit out front as either n goes to infinity, which is the same thing as delta x goes to 0, it accomplishes the same thing, then that approximation no longer is an approximation for the definite integral. It becomes equal to the integral from a to b of f of x dx. It's equivalent. Okay, so that's why areas are built on the same foundation as derivatives. It's because they're built on the idea of the limit. We can't physically make the number of subintervals be infinity, right? But we can mathematically. Now, I'm not going to make you do that actual limit process like we did with the alternate form or the limit definition, where I had you, set it up and expand it out, because you do have to memorize a couple of summation formulas. Like for instance, I'll use this as an example. If we looked at the sum from I equals 1 to n of I to the first, okay? This is a pretty common formula. If you want to know what this formula does, just go ahead and expand it out. And this is the video that y'all watched when I was out sick on Tuesday or Wednesday. You start with 1, you plug it in for I, and you get 1. It's a sigma, so it's plus. And then you go to the next value of I, which is what? 2, right? Because your index, as we call it, that's what I is. It's an integer, so you count. So now you plug in a 2 and you get 2, and then you go plus because it's sigma, and then the next integer is 3, and you keep going until you get to whatever n is. N can be specified as an upper bound. So this is the formula for the sum of the first n positive integers. Okay, and man, is there a formula for it? We know we can generate it. Like if I actually told you n was 3, right? Then that would just be what? 1 plus 2 plus 3, which is 6. It's pretty easy. But what if n were 100? Boy, then you'd have to expand out the first 100 and add them up. That would be kind of arduous, right? Well, it turns out that the great Gauss, there's a story that goes behind it. I don't know what grade he was in, but he's on the wall over there in the red poster. I think he was like, let's say second grade. It was something kind of crazy. And his teacher, was feeling like I am kind of today, but didn't have as much sisu. And so he just told the kids, hey, add up the first 100 positive integers, right? Or as they knew them, numbers, right? They didn't know there was anything else. Add up 1 plus 2 plus 3 plus dot, 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 plus 98 plus 99 plus 100. And the guy thought that it would keep his kids busy all day long. Well, Gauss came up like less than a minute later and showed him the answer. He had written on his slate board the number 50/50, and he showed it to his teacher, and his teacher's like, what is that? And he's like, that's your answer. And he's like, I guess the teacher didn't even know the right answer, right? He didn't expect anyone to answer it. And what Gauss realized that at early on is that there is, you can actually, there's a formula for it. The formula, which he developed, is n times n plus 1 over 2. So when you define things recursively, that's one thing. You can find the sum, and then to get the next value, and for n, just add the next number to it. But if you can find a formula where you could just directly substitute in, that's pretty impressive, right? So for us, I'm sorry, I'm using, yeah, for us, when n was 3, right, we just added up 1 plus 2 plus 3 was 6. But what do you get when you plug a 3 into that formula? 3 times 4 is 12, divided by 2 is 6. It works. But what if n is 100? That's 100 times 101 divided by 2. Well, that's 50 times 101, which ends up being 50/50. So it's you could do it by formula. So Gauss supposedly found that in second grade. So in order to do the limit as n goes to infinity for these Riemann sums, you have to have a couple of those formulas memorized. Now, before I leave the story, there's a real easy way for you to appreciate kind of how he thought about it. His teacher wanted him to add those up, but Gauss was like, you know what? I'm going to not just add them up once. I'm going to add them up twice. Okay. But this time I'm going to add the second sum in reverse order. 100 plus 99 plus 98 plus dot, 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 plus 3 plus 2 plus 1. And then he says, you know what? I'm not going to add them up left to right. No. I'm Gauss. I'm going to add them up vertiminously. And so when you add them up vertically now in columns, you get 101 plus 101 plus 101 plus 101 plus 101, so on and so forth, plus 101. And of course, Gauss knew all about repeated addition being multiplication. So we have the same number here added up how many times? There's 100 of them, right? So how do you add up 101 100 times? You do 100 times 101. And then Gauss was like, but you know what? I did add the sum up twice. So that's going to be twice as big as the teacher wanted. So I'll fix that by just dividing by 2. N times n plus 1 over 2. Pretty genius. Okay. So anyway, hopefully now at least you understand a little bit better those types of questions with the sigma notation. So, I mean, if you're actually taking the AP exam, will that show up? There might be one multiple choice question like the one in y'all's quiz. And if it is, hopefully now you can get it money in the bank. Yeah. All right. Let's retreat then and finish answering number 14. I said we would, right? This is a good opportunity to look at what's going to be known as U-substitution. So remember what we're doing is we know that each of these lobes for sine and cosine are one value apiece. All right. What will be the integral then from 0 to 2 pi of sine of x halves? Well, first of all, let's think about this. Let's graph Sahala. Sahala looks like this. Here's 2 pi. What does replacing x with x divided by 2 do to any function? That's the same as 1/2 times x. It's a horizontal what? It looks like a compression, right? Because a half is smaller. But remember, if it's on the inside with the x, it's actually a stretch. So it's a horizontal stretch by a factor of 2. So now it's going to look like this. It's going to hit the high point at pi, and it's going to come down. So it's really half of a cycle. Okay. So that's what the graph looks like. So the question is, what is this area here if we know that each of these blue areas are 1 unit? We saw over here yesterday that if I vertically stretch it by a factor of 2, it simply doubled the area. It wasn't geometrically intuitive, but it did work out that way. I can't just pull the 1/2 out in front here, can I? Because it's inside the angle. I guess I can try to use some half angle identities and try to make that, but no. So, God, what do you think it's going to be if you had to guess? Would you think it's the same size, or would it be twice as big? See, if they both reach to the same height, right? They both reach the height, but if this blue region here, I'll double highlight it. If that little blue region is 2 units, then if I stretch it horizontally, does the area stay the same? Certainly it doesn't stay the same, right? Because you think it stays the same as 2? It has to be more than 2, right? Because it's going up to the same height, but now it's over twice the interval. You think, yeah, you might think it's twice as much, right? But there's no geometric proof or reasoning why that should work. But let's see. Here's what we're going to do. This is called U-Substitution. And we're going to do this in 4.4. So here's your introduction to it. U-Substitution is basically this. Let this arbitrary variable u, just a dummy variable, let u equal your inside function. Okay, now the fact that I'm saying inside function means that we're starting with what's called, again, a composite function. A composite function is like f of g of x, right? It's something inside of something else. So what is my inside function here? It's not just sine of x, it's sine of a function of x, x over 2. So here's what we're going to do. We're going to let u equal 1/2 x. Okay. Now what we're going to do is we're going to change all of the variables that are x variables into u variables. So let's come up here and see what the x's are. This is from x equals 0 to x equals 2 pi, and this is dx. So I'm going to have to replace 1, 2, 3, 4 different things. Okay. So let's see if we can get to that. We'll kind of make this new integral. I'll even use a new color. It's going to be the integral. Sine is still going to be sine. But let's do the obvious replacement first. Instead of sine of x over 2, if I let u equal x over 2, it's now sine of what? U. Sine of u, right? Or your sine. Now I want to replace the dx. So how are we going to replace the dx? Well, that implies the derivative. So what I'll do here is I'll take the derivative of both sides with respect to x. So the derivative of u with respect to x is 1/2, right? And now if I multiply both sides by dx, I get du equals 1/2 dx. This, remember, is what we called in 3.7, this is what we call differential form. Okay, you don't have to, you could have gone straight to that, du equals 1/2 dx, or take the derivative Leibniz notation and multiply both sides by dx. I can solve that for dx now, right? So what does that mean? That means dx equals 2 du. So let's replace that. So on the back end here, my dx becomes 2 du. And now the last thing I have to replace are these intervals of integration. So let's do that. When x equals 0, I'm going to plug it into this formula here. Okay. When x equals 0, u is what? 1/2 times 0, which is 0. So that's going to be this new lower bound, which is really the same. And then on the other one, when x is, it was 2 pi. When x is 2 pi, u is 1/2 of 2 pi, which is what? pi. So it looks like that. That would be the new integral. Okay. I've just substituted my inside function for a single variable. And now it's not composition anymore, is it? It's not sine of blob. It wouldn't be a chain rule problem anymore. I was taking the derivative. It's just sine of a single variable. So that's called changing the variables using U-substitution. Now, this 2 is a writer. He's a constant multiple. I can pull him out front. So this becomes 2 times the integral from 0 to pi of sine of u du. And now I can focus on what this is equal to. Well, do we know what that's equal to? At this point, it might as well be sine of p dp, right? Or sine of q dq. Dq. Dairy Queen. Or sine of t dt. Or sine of x dx, right? As long as these two variables match, it's the same integral as son of a booger. What is the integral from 0 to pi of sine of variable d variable? The integral from 0 to pi of sine of variable d variable is 2. So I can substitute a 2 in there and I get what? 4. So there it is. It was 4. It was 4. That's called U-substitution. We just changed the inside function from a function of x to a single variable, and then we changed all the variables. Now that's going to be it's going to make a lot more sense when we get to 4.4. Okay, it's going to be actually pretty routine. Right now, it's like, what did we just do? And it feels weird. Now we could have done the same thing over here. Let's backtrack. If you didn't want to think about part F as, a horizontal shift, it's not just sine of x, is it? It's sine of blob. So let's see if we get the same answer if we do this. Let u equal x minus 2. All right, I'll let it happen. Let's go ahead and change the integral then. Down here, I'm going to have the integral of sine of, not x minus 2, but sine of u. So I got that piece changed. Let's go ahead and work on the dx. To get the dx, I need to take the derivative of u. So I'll do it in differential form. du equals 1 dx, or du dx equals 1, right? And multiply both sides by dx. Are you okay with that? So that's a straight exchange. So dx is du. So boom, that's a straight exchange. And now all I got to do is change my intervals of integration. This is from x equals 2 to x equals pi plus 2. Well, let's plug it in. When x equals 2, I plug it in right here. What is u? I was like saying it like that. When x is 2, what is u? U is 0. Boom. And when x is pi plus 2, what is u? It's pi plus 2 minus 2, which is pi. So there is the change in variables. So now I have the integral from 0 to pi of sine of u du, which might as well be the integral from 0 to pi of sine of pick a letter, d, pick a letter, including x, which of course is what? It's 2. And that's the same thing we got when we thought about it in terms of horizontal shift. Okay. So that's called U-substitution. And it's like the chain rule in reverse. Okay. This is like the reverse of the chain rule. Okay. Which, remember, the chain rule is for composite functions. U-substitution is going to be one way we can handle the antiderivative or the integral of composite functions. All right, now back to these, right? What would be the integral from negative pi to pi of sine? Well, let's see. That was a little bit. Here is Sahala, but now here's negative pi to pi. Is it 2 or 0? 0. It's 0 because the magnitudes of the areas are equal, but they're opposite signs. So this is 0. Now, this is an interesting little summary we can do right away here. Sine is what type of function, even or odd? What type of symmetry does it have? Y-axis or origin? It has origin symmetry. Y-axis is cosine. That's folding symmetry. Origin symmetry is rotational. Flip it 180 degrees, it looks the same, right? So if you ever have the integral from negative a to a of an odd function, what should the answer always be? It should always equal 0. Because of the origin symmetry, you're going to always have equal magnitudes, but always opposite signs, as long as it's on a symmetrical interval from negative a to a, always. Okay. In this case, it was negative pi to pi. That's kind of interesting. That doesn't work for an even function. An even function, instead of it canceling, it doubles what it does from 0 to a. We'll talk about that a little bit later. Okay. Now I'm switching to cosine. Well, that's not a big deal. I know what cosine looks like. It's chala. So here's cosine. And here's pi right here. So what would be the integral from 0 to pi of cosine? It's 0, because now I'm talking about 2 half lobes. Oh, I'm sorry, I misspoke over here. These are full lobes, so that's 2 and 2. My bad. But it's still 2 minus 2. These are half lobes, so these are equal in magnitude, but now from left to right, they're opposite in sign, so this also equals 0. And then finally, what is cosine from 0 to 2 pi? Here's an area of 2 below. Here's a half lobe, and here's a half lobe. Haha, yeah. The area would be 4, right? 2 above, 2 below, but the net accumulation is 0. And notice my areas are obviously not drawn to scale, right? That first region that I called 1 looks like it's 10 times bigger than the one below that I called 2. But numbers don't lie. Okay, so there you go. That was worth finishing because we got to learn a little bit about U-substitution. U-substitution. Okay. Let's do a U-sub right here before you even know why we're doing it. Let's say that I have the integral of the square root of 2x plus 1, and I'm going from 1/2 to 3. No, and hang on, that's too fancy. Let's just call this x plus 4, and we'll go from 5 to 12. Okay, dx. Go ahead and using the substitution, sometimes you're told this, using the substitution u equals x plus 4, find the new integral in terms of u. Okay. Later on, when we get to 4.4, you'll choose x plus 4 all on your own as u, because it's not just the square root of x, it's the square root of blob. And you're going to always let u equal the inside blob. But there's multiple choice questions out there where they give you a question literally like this, and they tell you the substitution, and then your answer choices are just integrals with different numbers. So go ahead and try that one, and then we'll move on to the next section. Okay, so before I change the variables, just to kind of see what it is graphically that we're doing, the definite integral from 5 to 12 of the square root of x plus 4 with respect to x would be equivalent in this case to find the area of that shaded region, because the square root of x plus 4 moves the graph of the square root of x to the left 4. So that's where its genesis point is. And then it is entirely above the x-axis, and we are integrating from left to right. So that net accumulation does also represent that area. But knowing how to evaluate a definite integral, we still can't do it, because in order to evaluate the definite integral, we're going to have to be able to find the antiderivative of the square root of x plus 4. Do we know what the antiderivative of the square root of x plus 4 is? No. If it were just the square root of x, then we could call it x to the 1/2 and just use the power rule, right? but because it's x plus 4 to the 1/2, that we can't just anti-differentiate that, and we can't expand it because we can't expand to the 1/2. So this is where U-substitution comes in handy. If I could just make that the square root of x, or the square root of a single variable, then I'd be able to use the power rule. So that's what we're going to do. So let's get our running integral going over here. We're going to let u equal x plus 4. So it becomes the square root of u. And if you want to check off f, you go. We got that. Now we're going to need dx. So I'm going to come over here and I'm going to need the derivative. So if u is equal to x plus 4, let's take the derivative of both sides. So the derivative of u with respect to x is 1, which now means du equals dx. And again, you can go straight to du equals dx. That's differential form. Or you can use Leibniz form and then multiply both sides by dx. But once again, dx is equal to du, so I can just make a straight replacement there. And then the last thing I need to do is change the intervals of integration. So when x is 5, plug it into there. And what is u? 9. And when x is 12, you get 16. And that's it. We've changed the variables. So now notice what we essentially did graphically, and this is kind of a nice thing to visualize. If we now take the square root of u, which might as well be the square root of x, and we find the area now from 9 to 16, we have to go out a little bit further. We're saying that this shaded area here on this graph is the exact same as the area of a different function over a different interval. They're equivalent, okay? But what can we do now that we couldn't do before? Well, I can find the antiderivative of this, because let's come off to the side here and write this as u to the 1/2 with respect to u from 9 to 16. And even though what we're about to do is technically the next section, I've already told you how to do it. If we can find the antiderivative of u to the 1/2 with respect to u, we know how to handle the 9 and the 16. Well, by the power rule, that's going to become u to the 1/2 plus 1, which is 3/2, and then we'll multiply by its reciprocal, 2/3, right? Now, if it were just an indefinite integral with no 9 and 16, we would put plus c and we'd be done. But in this case, it's a definite integral, so we don't even need the plus c because it's going to cancel. So we put this intermediate step and we read that evaluated from 9 to 16. And now here's where the next section comes in. The fundamental theorem of calculus tells us that I can evaluate it by plugging in the top minus plugging in the bottom. Plug in the top minus plug in the bottom. Now here's also what I'm going to try and get you to be in the habit of doing. When you have a constant multiple like that, you can either A, take it through with you to each term, or again, get in the back of the truck 2/3 times, and now it becomes just 16 to the 3/2 minus 9 to the 3/2. That's how we evaluate it. And that way we don't have to get that fraction involved. Now let's simplify this, because this does have ramifications on the AP classroom quiz. 16 to the 3/2 power. We should be able to evaluate that without a calculator. That's the same as 16 cubed, and then take the square root of it, or take the square root of 16 and then cube that. Go small before you go big, right? So 16 to the 1/2 is the square root of 16, which is 4, and then 4 cubed is 64. Yeah. 9 to the 3/2, instead of 9 cubed and then square root it, we'll square root it first to get 3. 3 cubed is 27. And yeah, I'm running out of room. I'll just come up here. Long equal sign. 2/3 times, what is this going to give me? 37. And now 37 divided by 3. Go small before we go big. Now it doesn't go in. But it does multiply by 2, right? 74 thirds. 74 thirds. Wow, that is the value of both of those regions. But the one on the left, we couldn't do. So that's really the power of U-substitution. It takes a composite function and turns it into just a singular function. Now, when we get to 4.4, I will show you that in this case right here, you're not even going to need to go through U-substitution, because I'm going to teach you another way called pattern recognition. And you'll recognize the pattern and you'll be able to answer it a lot more quickly. But U-substitution is still going to work. And there's a couple of times where U-substitution is required, like when they tell you to do it, like we did here, or in another case. But anyway, that's that. That kind of ties up nicely 4.2. All right. So make sure you know Riemann sums, left endpoint, right endpoint, midpoint, right? With midpoint, you can do it if your subintervals are unequal widths, but they have to be the same width on consecutive intervals. And I actually saw an AP question several years ago where that was the case. It was like the width was 2, then 2, and then it was like 3, then 3, and it asked you for a midpoint. Trapezoidal, remember, know how to do that on its own. Also know that it's the average of the left and right. Anything else from this section that's worth talking about? Travel agent problems, right? Those are fun. Map your own itinerary from to. And then when you pull the values off, that's when you make them negative or opposite if you have to flip them. All right. I don't know if it's worth starting the next section, right? We only have like 10 minutes left. So why don't I let y'all work on either the AP classroom quiz if you're not done with it. Maybe you can answer question 5 now. The worksheet is out there. It's optional, right? Or use the rest of the period to ask me specific questions. And that way we'll start with 4.3, the fundamental theorem of calculus. And this guy, Isaac Barrow, we'll start with him on Monday. I'll be waiting for you. Okay.